Bismillahirrahmanirrahim. Assalamu alaikum. Here I am going to record the solution for assignment 2. There are many questions, about 18 questions, and I cannot solve all of those questions, but at least some questions and the similar questions one you can solve yourself. So we start with the first question, which is from chapter 6. Okay, the short questions you can find the answer in the book. Let's go to question number 7, which is about process scheduling. Okay, and it says that we have 5 processes. There is the burst time and priority, and then we have this description that they have arrived in this order: P1, P2, P3, P4, P5 at the same time. Okay, so the time is same at time 0, but this is the order. So if we are going to consider the first come first serve algorithm, then we should consider P1, then P2, P3, P4, and at the end it will be P5. Now in first come first serve, we are not going to consider the priority. So some students, or many students, they have started with P2 because they thought that priority is first. Now this is the first come first serve algorithm, so we will ignore the priority, we will not consider the priority. So we will always start with P1, then P2, and so on. Okay. Now the first question asked is to draw the Gantt chart, okay, then the turnaround time for each process, and finally the waiting time of each process. Okay, so the Gantt chart, I have drawn it for you. It looks something like this. Let me go to the solution. This is question number 7. This is the table. Okay, and we start with P1. The burst time is 2. Okay, first come first serve, so it will go to complete execution. P1 will finish in 2 time units, then P2 will take 1 time unit, then same for P3, P4, P5. Okay, so you can see the end time. The start time is 0 here, then the end time for each of these processes. Now the turnaround time, okay, everyone asked me what is the turnaround time, and they didn't understand. Now it's written clearly. Okay, if you see to this question somewhere before question, I have explained what is turnaround time. So it is the total time, which means the waiting time as well as the time in the CPU. That will give you the turnaround time. So we simply need to calculate the waiting time as well as the time in the processor. So for P1, it is the serving time is 2. And because it started at time 0, so the waiting time is 0. So 2 plus 0 is equal to 2. This is the turnaround time for P1. Similarly for P2, the time on the processor is 1 unit and it was waiting 2 units before it started. So this is 1 plus 2, which is equal to 3. For P3, the time on the processor is 8 and the waiting time is 2 plus 1. Okay, before P3 there was P1 and P2 for 3 seconds. So 8 plus 3 is 11. Similarly for P4 we have 4 plus 11, and for P5 we have 5 plus 15. That is the turnaround time. Now if you are asked what is the average turnaround time, okay, the average turnaround time will be for all processes. So you will add these processes: 2 plus 3 plus 11 plus 15 plus 20. Okay, so this is 46 and 5, this is 51. 51 divided by 5, so 10 point something. This is the average turnaround time. Okay, then the waiting time. Okay, so you already see the wait time, which is here on the right side. So 0, 2, 3, 11, 15. This is the waiting time for each process, and the average waiting time is 2 plus 3, 5 plus 11, 16 plus 15, 31. 31 divided by 5. This is 6 point something. This is the average waiting time. So that was the first question. Okay, the waiting time. In fact, the problem, you see that waiting time for each process, not the average waiting time. So you should remember, if you are asked for each process, you should just calculate for each process. If you are asked for average, then you should add all of them and divide by the number of processes. So that was about question number 7. Okay, then question number 9. Okay, let's go to this question table. So question number 8. You can see yourself. Question number 9 is this one. Okay, so you have this table, and then you have the questions about turnaround time, average turnaround time, and turnaround time if we change the quantum. Okay, so here we are using the round robin and q is equal to 5. Okay, so let's move to question number 9. This is the table. So because q is equal to 5, round robin q is equal to 5, so we can have at most 5 for each process. If it is less than 5, then it can quit before. Okay, it can do context switch. Otherwise, the context switch will take place only after 5 seconds, not more than that. Okay, so we start with P1 round robin. Okay, P1 is total time required is 19, but quantum is 5. So after 5 seconds, it will change. Then we have P2. Total time required is 12, but after 5 it will change. P3, because total time is only 3, so we will just change after 3, and we will give chance to P4, which is 9 required, but it will context switch after 5. P5, the required time is 21, but it will change after 5. So P1 comes again, because 1, 2, 3, 4, 5 they are finished, round robin, so P1 will come. Before it did 5, now it will do 5 more, so this will make 10. P1 will finish, then P2 will finish 5. P4, the total time was 9. P4, it did 5 before, the remaining 4 it did now. So after 4 it will finish. P5, it's 21, it will continue. Then P1 again, then P2, this time P2 is 2, because total 12. 5 one time before, then 5 again, and then 2 remaining, last remaining 2, it's done now. After P2, P3 and P4 they have finished, we will directly go to P5. After 5 seconds, it will go to P1, 4 seconds, the last 4 seconds, because after out of 19, it has already done 3 times. 15 done before, the last remaining 4, and then the final will be P5, and so on. So the wait time for each process, we will see for P1, okay, the first wait time was 0, okay, but then after 5 you can see that before finishing P1, okay, it finished here. So how much time it has waited? Okay, so P1 was waiting these 5 seconds, these 4 seconds. Sorry, I'm doing it for P4. Yes, okay, it's not for P1. So for P4, we are going to calculate all the time it was waiting. Okay, so it waited these times, which is 5 plus 5 plus 3. Okay, then it was on CPU. Then again it was waiting 5 plus 5 plus 5, and then it finished here. So out of these times is 5 plus 5 plus 3 and 5 plus 5 plus 5. This was the waiting time. Okay, and then we have the CPU time. So the CPU time it was taking was 5 seconds here and 4 seconds here. So this is 9 seconds. So total waiting time plus CPU time is 28 plus 9, which is 37 time units. Okay, that is the turnaround time for P4. Similarly, you can have turnaround time for P3 in the same way, which is 13. Now, this was one part which asked to calculate the turnaround time for P4. Similarly, you can calculate turnaround time for the other processes. Okay, and the average will be sum of all of turnaround time divided by the number of processes, which is 5. Okay, so whatever you get, I have just calculated P4 and P3. You can calculate for P1, P2 and P5. That were the first 2 parts. The third part says, the last part says that what is the turnaround time for P4 if time quantum is increased to 6. Okay, so before the time quantum was 5, now if we change the time quantum to 6, you can see how do these processes work, and at the end we find the waiting time plus the service time. Before, the service time was 5 plus 4, now it has become 6 plus 3, same 9, but the time quantum has changed. So instead of 5, we have 6 in the beginning and the remaining 3 at the end. So now this is 33 plus 9, which is 42, which means that from 37 the turnaround time has increased for this process when you increase the quantum time. Okay, but sometimes when you increase the quantum time, it will decrease. It depends. Okay, so that's about end of question 9. Now question 10 is about from chapter 7. It's about for the following graph, determine if there is a possibility of deadlock or no. Okay, and explain in detail. So first you see this these three graphs, okay, we have I've shown here. So you can see if we start from any node, we can see that there is only one resource and there is a cycle. So if there is a cycle, then there is definitely we can say that there will be a deadlock. Okay. In this case, do you see any cycle? Well, actually many students, they say there is a cycle. Let's see. So we start from T1 in this case, and we see there is a cycle. Okay. But the thing is that there are two resources. So we are not sure if there can be a deadlock or not, but it is not in the safe state. There can be a deadlock or not. In this case, some students said that there is a cycle, but there is no cycle, because if you start from any node, for example P3, and you come here, then you cannot go to the next one. Okay, why? Because the arrow is in this direction. So even if you start from here, you start like this, okay, and then you can stop here, you cannot go further because this is not a cycle. So you say that this is a cycle, but actually this is not a cycle. The cycle will be if all arrows, they were in the same direction, but here the direction changes. So there is no cycle and there is no deadlock. Next question is about question 12. I am just doing part 2, okay, but you can consider any part. So let's go to part 2, question 12. Question 11 is simple. There is nothing difficult, that's why I didn't do it. But question 12, let's see it. Okay, so it says I did part 2, but it's same as part 1. We have the following diagram that shows the main memory with the operating system and some other processes, 3 processes, and the blank or empty space areas, they show free memory. Okay, so this is the example. Now part 2, it says that for each process A, B and C, identify the base and limit of discrete values. So the graph is in front of you, this is the graph, and then you can see that from 0 to 260, this is the operating system. From 260 to 454, okay, this is not 455. Actually for 455, the empty hole starts, but here I have considered 455. In reality, this should be 454. So 454 is the limit. So 454 minus the starting, which is 260, you get 195. So 195 is the size, which is asked in the next part, but the starting is 260, the ending is 454. Here the starting is 600 and ending is 789. For process C, the starting is 790 and the ending is 884. The size of process C is 885. Okay, this is not 55. I have done it wrong. Okay, so let me delete it. It is actually 885. So let me delete it, change it so that you don't confuse it. So this is 800 and let me try 885 minus 790. So this is 95. Okay. In fact, I told you before this should be 884. 884 minus 790. So this is one more less, 94. Okay. So this is the size and the base and limit of each register. Okay. Then one question says, what will happen if process B generates a logical address of 200? Now you can see this process B. Its address size, it starts from 600 to 790, which is 190. Okay. So 190 is the size of the process. If it says to go to address 200, then this will be error, because it doesn't exist. For it, the maximum limit is 190, 200 does not exist. Okay, and the size of process B you can find as I explained before. After that, I have solved for you a question which is this question. I don't remember which question is this. Let's check it here in the let's wait. Okay, this question is question number 4, part 4 in 12, part 4. So it says consider the following 2 diagrams, left one for memory management unit and the right one for the main memory. Suppose process B is currently executed in CPU. So we are thinking about process B. It is in the CPU, and the CPU generates the logical address of 107. Okay, what values will be used in the 2 empty boxes? So 107 is the logical address, The relocation register is actually, because we have process B, so it should contain the value of 603, and the physical address will be 603 plus 107. Okay, so 603 plus 107, this is 710, that will be the address. Next, question number 13. We go to question number 13. Okay, so you are shown the diagram of memory with some processes and size of each process in memory as well as the size of in memory. When a new process comes, it must be allocated space in one of the free memory spaces. So you have free 1, free 2, free 3 and free 4 as the memory spaces. Okay, so that's the introduction to the question. Next, what we have is that which part I'm going to do, any one it is. So I have done this is 160, 355, 430, exactly. I don't know whatever it is, but if it asks that if a new process comes with 80 bytes. Okay, so this is the first example, I think. Which one? 60 bytes, I don't know, let me check. Yeah, 80 bytes, this is part 1. So there is a process which comes whose size is 80 bytes. So where will it go if you use first fit, best fit and worst fit? Okay, yes. So 80 byte process comes, we have free 1, free 2, free 3 and free 4. Okay, and here on this side I have written the possible or the allocated memory size. So free 1 has a size of 75 bytes, free 2 has 170 bytes, free 3 has 35 bytes and free 4 has 104. So if you consider first to be the free 1, then second to be free 2, etc., then first come first served, first fit will give free 2 to 80 bytes. Why? Because free 1 cannot be given, it's smaller. Then the next one available is 170. If you choose the best first will again choose, no, this time it will choose 104, because this is the smallest possible memory which can accommodate 80 bytes, and the worst fit it will choose the biggest one, which is free 2. Similarly, the next question is about 60 bytes. So for 60 bytes, the first fit will be 75, okay, the best fit is also 75, and the worst fit is free 2, which is the biggest memory size. Okay, so that was I think part A, and then for part B also maybe, okay, we can think about the internal fragmentation. So let's say if you have 60 bytes and you have first fit, okay, so 60 bytes first fit, it will go to free 1, okay, and 15 bytes will be the internal fragmentation, which is the remaining process. Okay, and then what is the total size of free memory in the system after this process is allocated? Okay, so here 60 bytes have been used, 15 bytes are remaining here, plus 170 plus 35 plus 104, this is the remaining total bytes. Question number 15. Let's go to question number 15. 14, it's just theoretical question you can answer. 15 says, given 6 memory partitions, okay, these are in this order. Okay, so the first is 300, then you have 600 and so on. How would the first fit, best fit and worst fit algorithms place processes of these sizes in this order? Okay, so it means that first we have to consider these memory locations, then we will consider the first fit algorithm, and these processes will come one by one, and rank the algorithms in terms of how efficiently they use memory. Okay, so this is the book question 8.11. Now very quickly I have redrawn this sizes. So here actually there is no diagram. I have created a diagram like this. So these are the memory partitions available to you. And then these processes come 115, so if it comes 115 comes, so it will go to memory location 1. So this is 1, 2, 3, I have given these locations. So 115 will go to partition 1 in the first fit, because we start from here. After that we have 500, okay, so it will go to partition 2, the next one available. Then we have 358, we cannot use 350, we cannot use 200, we will use only 750, which is available. Okay, and after that 200, I have written it 4 because we start from here. So 300, 115 has been used. Okay, remaining is 185. We cannot use 200. Here 500 have been used. Remaining is 100. We cannot use for this 358. This is also small. Sorry, 200. We are talking about 200. So remaining 185 is small. Remaining 100 is small. This was done. 200 we can assign here actually. Okay. So I don't know why I choose 5. This is first come we used. Okay, this is available. Okay, so I think if I'm not wrong, I made a mistake. So this should be going to partition number 3. Okay, if I didn't make any mistake. Okay. Anyway, similarly you can do for this best first and finally worst fit strategy. Okay, so whenever you assign, you have to see whatever is the remaining location. So actually when I use this, yeah, I know why 4. I choose 4 because when I choose before this partition, why was it 4? I don't remember why I did. Anyways, maybe I made some mistake. Okay, so this is how you can do the rest of those questions. Okay. Question number 16. This is a question. Consider a logical address space of 256 pages. Okay, so I have a logical address space which has 256 pages from 0 to 255, and the size of each page is 400 kilobytes. So you can see 400 kilobyte page and 256 pages mapped onto a physical memory of 64 frames. Okay, so this is the logical memory, and then I have physical memory which is RAM. So actually the RAM can be something like okay, I'm not sitting very well in the chair. Okay, that's very bad, but anyways, so this is my RAM. Okay, let me undo it. Okay, let me try to make a clear picture. Okay, so let me start from here. Okay, and then I go down here until here. So discard the space. Okay, so let's say these are the frames, and each frame size is whatever it is, but you have a total number of 64 frames. So this starts from 0 to 63. Yeah, this is from 0 to 63. We have this. Now it's not written what is the size of a frame. The thing is, we have normally the page size and the frame size to be the same. Okay, but because here we see that the size of page is 4 kilobytes and we have 256 pages, but we have 64 frames only. So it means that in these 64 frames we have to map 256 pages within these. So it means if you see in one frame we will have 4 pages. Okay, what I see is that 256 divided by 64, this will give you 4 pages in one frame. Okay, so that's how we are going to do. Now what I did is that the first question is how many bits are required in logical address. Okay, now logical address we have 256 pages, which means that 2 power 8 bits are needed for maintaining the number of pages, and the size of each page is 4K, which is 4 kilobyte. 1 kilobyte is 2 power 10, 2 kilobyte is 2 power 11, 4 kilobyte is 2 power 12. Okay, so 2 power 12 means we need 12 bits for the size of a page and 8 bits for the number of pages. So total we have 8 plus 12, which is equal to 20 bits for the physical, for the logical address space, which is this. So 20 bits will be needed to save this process, logical address space. The second question is how many bits are required in physical address. Okay, so this 4K 2 power 12, how did it come? I have explained it here. How 2 power 12? Because 4K means 4 multiplied by kilo, which is 2 power 10. Okay, so 4k is 4 into 2 power 10. 4 is equal to 2 power 2. So this is 2 power 2 multiplied by 2 power 10. This is equal to 2 power 2 plus 10. This is equal to 2 power 12. So this is 4k. I have explained it here. So let me make an arrow from here to here. Okay. The second part is how many bits are required in the physical address. So as I said, we have 64 frames and we have 256 pages. Okay, which means that how many address spaces are for frames. So for 64, this is equal to 2 power 6. Okay, 2 power 6 is 64. So we need for these many 2 power 6 possible frames. Okay, which means 6 bits will be needed to represent the frames. And because we have 4 pages in one frame, okay, and the size of each page is 4 kilo, so this means that for each frame we will have 4 multiplied by 4 kilo. This is equal to 16 kilobyte, and 16 kilobyte is 2 power 14. Just like here, 4 kilobyte is 2 power 12, 8 kilobyte is 2 power 13, and double that again, 16 kilobyte is 2 power 14. So which means 14 bits will be needed for one page. So for 14 bits we will use one page, for every page 14 bits, and for total number of frames, which is 64, we will have 2 power 6 possible values, which is 64. So 2 power 6 and 2 power 14, okay, 14 bit plus 6 bit, this is 20 bits. So we will need 20 bit for this physical memory. Before we needed 20 bits for logical memory, now we also need same 20 bits for physical memory, just the mapping is different. Here we have how many? 8 bits for pages and 12 bits for address. Here we have 14 bits for addresses of one page and 6 bits for the pages. Okay, you should think about that. If you don't understand, pause the video and listen it again to understand that. Finally, question number 18. Okay, so question number 17 is about processes. You should know this. And question number 18 is that you have physical memory and there are addresses A to P. Okay, so how can you assign those addresses to physical memory? So this is logical memory from 0 to 16. These are 4 pages. Each page is 4 bytes. Okay, and there are 4 pages, which means that we need 2 bits for each page, because 2 power 2 is 4, and we need 2 bits also for page, because 2 power 2 is 4 here. So 2 power 2, we need 2 bits for page size and 2 bits for page number. And remember, this is always we are talking about 2 power. Why are we talking about power of 2? Why not 3, etc.? This is an important question for managing pages. So the answer is because the computer works in the power of 2. Because each bit, the base is bit, and each bit can have only 2 possible values. So if we choose 1 bit, it is 2 power 1. If we choose 2 bits, it's 2 power 2. If we choose 4 bits, it's 2 power 4, and so on. So we are choosing power of 2 for pages. Now here there are different ways you should understand. First, I show you that there are 4 pages, page 0, page 1, page 2 and page 3, and each page has 4 addresses. Okay, and page 0, in the page table we can see that page 0 is in frame 5, which you can see that this is frame 0, frame 1, frame 2, frame 3, frame 4, frame 5, 6, 7. So 8 frames are there in this memory. Okay, so this is from 0, starting from address 0 to address, last address will be 31. Okay, 32 possible values from 0 to 31. This is the size of physical memory, and logical memory is 16 bytes. Okay, so I was talking about page 0 in frame 5. So this is ABCD, which is page 0. Now page 1, which is EFGH, it is in frame 6. So EFGH. Okay, if you are going to find the address of one particular instruction, for example J, which is 9. Okay, so the address 9, this is logical address. Okay, what is the physical address? Now we know that address 9 is in page 2 and the offset is 1. Offset 0 is 8, offset 1 is 9, offset 2 is 10, and offset 3 is 11, from 0 to 3. These are the addresses. So page 2, offset 1. This is what we know from the location of J. Page 2, offset 1. Page 2, we know it is in frame 1. So we will go to frame 1 at offset 1. Frame 1 is here, offset 1 is this one. This will give us the location of J. Also the address of J we can find because frame 1 and each frame size is 4. So 1 multiplied by 4 will give us 4, plus the offset is 1. This will give us the address of 5. So absolutely we can go to address 5 directly. So from page you can go to frame, and within offset you can find this address, frame 1, offset 1, or absolute address is you will multiply by 4, which is the size of the page. Okay, so if this was 2, you multiply 2 multiplied by 4, 8 plus 1, 9. Okay, which will be this address of n. Okay, and n, if you can see here, this is here 13. So from 13 you go to page number 3. Okay, which is frame number 2. Okay, and then it is the second one here, offset 2, offset 2. So you can use this method to find the page and the offset. So that was all about assignment 2. Okay, I hope you understand it, and best of luck for your exam. I have already uploaded the details of the exam. So chapter everything is going to come in the exam, not just these questions. For example, here I'm not talking about page replacement algorithms in this assignment, because when we did the assignment we had not studied the page replacement algorithm, the least recently used, etc. So that's also in the exam, don't forget about that. Okay, so best of luck for the exam, and I wish you an excellent future. Assalamu alaikum.